Assalamu alaikum. So, inshallah, today I will continue the revision with chapter 6. Chapter 6 is dealing mainly with the second law of thermodynamics and its application for heat engine and refrigeration cycle. So, actually, the second law of thermodynamics has two main uses. The first use actually is that it deals with the quality of energy and the direction of any process. It says actually any process has to proceed in a certain direction from the high energy level or high energy quality to the low energy quality. Unlike actually the first law of thermodynamics, second law of thermodynamics deals with the logic of the process, and it says actually if any process is a valid process or not. And any process, the condition is that any process has to proceed from the high energy level or high energy quality level to the low energy quality level. The first law of thermodynamics has nothing actually to do with the logic of the process or the direction of the process. It is only an energy balance, energy input to the system equal to energy out plus the change of energy equal to energy input to the system minus energy out equal to the change of energy of the system. This is the first use of the second law of thermodynamics, that we can specify a direction of any process. The second use actually of the thermodynamics, it can calculate the theoretical or the maximum theoretical or maximum limit of a given device. So for a given device, using the second law analysis, we can calculate what's called the maximum efficiency or the maximum coefficient of performance. And in this case, we can compare it actually with the actual value, and then we can see the difference between the maximum efficiency, maximum possible efficiency, and the actual value, and then we can have indication about the friction losses within the system. Also, if you are getting a new device or something like air conditioning system or any other system, and you do have actually, it is written on this system or offered for you actually that this system is given a certain efficiency or certain coefficient of performance, then in this case we can apply the second law of thermodynamics, and then we can calculate the maximum efficiency of this system. So the actual value, which should be as a given value for you, should be less than actually the maximum calculated efficiency. If the reverse actually, if you do have an offer with an efficiency greater than the limit or the maximum value, so this offer is not okay. So also we can, as we said, we can calculate the maximum efficiency of this device and to compare it also with the actual value to see actually the difference between both of them, which give indication about the losses within the system. In this chapter actually, the second law of thermodynamics, it deals actually with two main applications. The first application is the heat engine, what we call actually a heat engine, and the second application is the refrigeration or heat pump cycle. Refrigeration is actually the same as air conditioning, so the same concept is applied for refrigeration or air conditioning cycle, which is actually the main purpose of this refrigeration cycle is to cool down a system, cool down like a food compartment or something. The main subject also, the main purpose actually of working of air conditioning system is to cool down the surrounding air. And actually heat pump, it is working on the same cycle like refrigeration cycle, but what we need from this cycle is the heat up, not cooling down. Both of them actually, heat engine and refrigeration cycle and refrigeration system are working on a cycle. So this system is working on a cycle, and also the refrigeration system is working on a cycle. The main difference between the heat engine and the refrigeration cycle, the heat engine actually converts the heat into power or into work, but actually the reverse is the case of refrigeration cycle. It converts the work actually into controlling the amount of heat removal from the system in case of refrigeration system, or the amount of heat rejection in case of heat pump. Let's consider actually one by one, and let's do the analysis for both of them. So first of all, let's start with the heat engine. So in case of heat engine, it converts actually, as we said, it converts the heat into work. So if you do have any heat engine working on a cycle, so it receives actually Q high, heat is added from high temperature source, and part of this heat actually is rejected at low temperature to low temperature sink. That's why we call this heat transfer as Q low. and based on that we can have actually some work out of this system. So the main function of the heat engine is to convert the heat into work. Part of this heat actually is rejected also at low temperature. The most common actually example for the heat engine is what we call actually the steam power plant, which is the simple cycle for a heat engine. The steam power plant consists of pump. We do have the water is being actually pumped using this pump, so its pressure is being raised to the boiler pressure. Then inside this boiler actually is usually connected to a furnace. So in this case we do have the heat of combustion. Inside this furnace is added to the water to heat up this water or boil this water. So the water will be converted in this case to steam at high pressure and high temperature, which means actually steam at high enthalpy. So we just pass this steam through a turbine, so that actually this steam is fixed first through a fixed blade which is called nozzle. So the flow is forced with high velocity heat, so actually it can hit the blade of the turbine, so actually the shaft of this turbine will be rotating. Then we can get work out of this turbine. The steam leaving this turbine usually at saturated state, so still we do have mixture of steam plus water. In order actually for the system to work on the cycle, we have to get back actually to the initial state, which is the water state. So in this case, we have to reject actually this some heat inside the condenser from this actually saturated mixed steam mixture. So part of this heat is rejected through a cooling system on something in a power plant. We just cool down actually this steam in a condenser. So part of this heat will be rejected. So actually all of the steam here will be condensed and getting back actually to the same initial state, which is water. So in this case, the cycle actually can be repeated again. This water can be pumped inside this pump. We do have work input to this pump. Then we can raise the pressure of this water, add heat here through combustion or furnace or something. We can actually boil the water to steam, and again we can generate work, and the cycle is repeated. But for any actually heat engine, as we said, for any heat engine, it should work, as we said, to generate continuous work. It should work on a cycle. Working on a cycle means actually we start from a given point, which is the inlet condition, doing actually series of processes and getting back to the same initial point. Type. In case of working on a cycle, in this case, as we're starting from a certain point, doing actually those processes and getting back to the same point. So this means actually the initial state is the same as the final state. So this means actually the initial energy is the same actually as the final energy. So this means that change of energy through the system or through this cycle should equal to 0. If you apply the first law of thermodynamics, it should be Q net minus work net equal to the change of energy of the system. Change of energy of the system for this cycle is equal to 0. So for any working cycle, we should have Q net is the same as work net. Q net actually mean actually the net heat added to the system, so which is equal to Q high minus Q low. So this is Q net, Q high, Q added minus Q rejected is the same as work net. Work net is the work out in this turbine minus the work input in this pump. So in general it will be equal to work out minus work input to the system. So for any system working on a cycle, we should have Q net heat transfer to the system is the same as work net. But in this case, actually for a heat engine, to evaluate its performance, we can calculate actually the thermal efficiency of the system. Thermal efficiency is equal to work net divided by the heat added to the system. Work net is the net work, not actually the turbine work. It is the net work, is the difference between the turbine work minus the pump work. Divided by what we give to the system, actually what we provide to the system is Q high, which is the initial input. Efficiency is the output, net outcome divided by the input, the mean input to the system. As we said, work net is the same as Q net divided by Q high. Q net is equal to Q high minus Q low. So this efficiency will equal to 1 minus Q low divided by Q high. And this is the efficiency or the thermal efficiency of a heat engine. So for any heat engine working on a cycle, The thermal efficiency is equal to work net divided by Q high, and it is the same as Q net over Q high, and we do have it should equal to 1 minus Q low divided by Q high. And actually for any heat engine, this efficiency, the thermal efficiency should be less than 1. And this is actually the first statement of the second law of thermodynamics, which is the Kelvin-Planck statement applied to any heat engine. It says actually we cannot design any heat engine without heat rejection. So as we should have actually heat rejection for any heat engine, part of the input heat is rejected or lost. So this means actually the efficiency should be less than 1. If we rephrase actually this statement, we can say actually we cannot design any heat engine with efficiency equal to 100%. So if you do have a dealer or any other actually heat engine is offered for you, so in this case if the efficiency is equal to 1, so actually this is totally wrong, because the concept of operation of any heat engine is that we should reject some heat. We should have some heat lost in the system, which is Q low, and based on that, as we should have some heat is lost, so this means actually the efficiency should be less than 1. But actually this heat lost is not related to friction or anything within the system. Just it is related to the concept of evaporation. We have to reject this heat. We have this heat already. Before actually passing the steam saturated mixture through the condenser, the system still have this energy, which is Q low. But we have to reject it in order actually to reach the same initial state, which is water. In order to work on a cycle and generate continuous work, we have to get back to the same initial state, which is water, not steam here. So we have to reject this heat, get rid of actually this heat, so that we can get back to the initial state. Now we are working on a cycle, so that we can generate continuous work, and then we can repeat this cycle. But without this condenser, we cannot actually work on a cycle. So it is not something related to friction within the system, but it is related to the concept of evaporation. We have to reject some heat in order to work on a cycle and generate continuous work. And as we have to lose some heat, so in this case the thermal efficiency of any heat engine should be less than 1. This is regarding the heat engine, which is the first application of the second law of thermodynamics. Let's move actually to the second application of the second law of thermodynamics, which is for refrigeration or heat pump system. So for refrigerator, which is the same as actually heat pump, refrigerator or heat pump are working on the same cycle. So when I say refrigerator, this means also my torque is applied to air conditioning. Okay. Heat pump is the same as actually as the refrigeration cycle, as we will show right now. The main function of the refrigeration cycle is actually we do have input work and convert actually this work into control of the amount of heat absorbed in the refrigeration cycle or heat rejected in case of heat pump. Let's consider the refrigerator, if we do have any refrigerator. So in this refrigerator, the main function here actually is to absorb heat from low temperature. So see this concept, it absorbs actually through Q low. In this case we don't have the heat is rejected at low temperature. In this case heat is added to the system at low temperature, from low temperature say. So we absorb the heat from low level and we reject actually this heat Q high to a high temperature source at higher temperature. So in this case, based on the second law of thermodynamics for a direction of this process, it says any process should proceed from high energy potential to low energy potential. Now we are doing the reverse. Heat is transferred from low temperature level to high temperature level, which is not actually really the case. This is not true. This is not true unless actually we do have what? We do have work input to the system. So we have to add work input to the system for the working fluid inside, in order actually to raise its energy level so that the heat can transfer from the low level to the high level. And this is the second statement of the second law of thermodynamics. In this chapter you can just revise the statement, which is called the Clausius statement. Clausius statement of the second law of thermodynamics, it says you cannot actually design a refrigeration system without work input to the system, because actually we cannot have heat transfer from the low temperature to the high temperature level. So the second law of thermodynamics, which is Clausius statement applied to refrigeration system, you cannot design actually a refrigerator without input work to this refrigerator. Right, let's look at actually the refrigeration cycle, which we do have like the fridge at your home or something. This is the simplest example. So in this case, we do have the evaporator, or what we call actually the freezer, which is existing. We do have the Freon. In most of the cases, it is Freon 134A. So in this case, the Freon inside, it absorbs actually the heat from the low temperature source. Low temperature source actually, which is the freezer, as we said, or the evaporator, is called the evaporator, which is existing at low temperature. And also, even though actually Freon is still at lower temperature, passing inside this freezer. However, the freezer is existing at low temperature, but Freon, which is passed inside the freezer, is still at lower temperature. So it can absorb the heat from the food compartment at low temperature, and this Freon will be converted to vapor. And then actually at the back of the fridge you will find actually we do have a compressor, and this compressor is connected actually to an electric motor, and this electric motor is connected actually to the socket to have electrical input power, and this is the source of power consumed in the electrical motor that is driving the compressor. So at the end we do have work input to this compressor to compress actually this Freon. Now the Freon will be converted. We do have Freon vapor at high pressure and also high temperature. Then actually we do have the condenser, which is actually the set of hot wire in the back of the fridge. You see actually we do have set of hot wire. This net of hot wire actually is called the condenser. So the idea here actually is to cool down the Freon by rejecting some heat actually to the high temperature surrounding. The surrounding temperature in this case is called the high temperature because the evaporator temperature is very low. So this is actually the surrounding temperature existing at high temperature. Part of this heat actually of Freon is being rejected to the surrounding air through air cooling. So in this case the Freon will be converted back. Most probably it will be converted to liquid. Still actually it is at high pressure, but actually, and also its temperature is still a little bit also we can say high, but it has been converted from the vapor state to the liquid state. Then we can pass actually this Freon through what we call the capillary tube or expansion valve or throttling valve, and in this case we do have actually much drop in pressure through this capillary tube, with the area of in the flow direction is restricted too much, so that actually you should have high pressure losses, so the pressure will drop actually down too much, and also the temperature will get down too much also. So in this case now we do have actually liquid Freon existing at low pressure and low temperature. So now we can repeat the cycle. It can be passed through the evaporator again so that it can absorb the heat from the food compartment inside your fridge, and then actually it will be converted again to vapor, and again this vapor actually is being compressed inside this compressor, which should have actually work input to the system in this case, and then we can actually repeat the cycle again. To evaluate actually the performance of this system, just to evaluate actually our need from this system. So in this case we don't have efficiency, but we do have what we call the coefficient of performance. So the coefficient of performance of the refrigeration cycle, what we need actually from the refrigeration cycle is to do what? Just to cool down the food compartment. If we do have food or something, just we need actually to cool down. So what we need actually is Q low. So the coefficient of performance will equal to Q low, what we need from this system, divided by what we give to this system, the initial input, which is our input, the net work into this system. So it's equal to Q low divided by work in it. As we said, for any for any refrigeration system or air conditioning system or heat pump or even heat engine, any of those systems is working on a cycle. So the same we do have Q net is the same as work net. So in this case we can just say the coefficient of performance of the refrigerator will equal to Q low divided by, instead of work net it will be Q net, which will equal to Q low divided by Q high minus Q low, and this is actually the coefficient of performance of the refrigerator, and this value may be greater than 1. It is unlike the thermal efficiency for a heat engine. Thermal efficiency of heat engine should be less than 1, but in this case the coefficient of performance of the refrigerator may be greater than 1 in this case. This is not an efficiency. This is regarding the refrigerator. In case of heat pump, this actually item, which is called heat pump actually is the same as refrigeration cycle. It is exactly the same cycle, but what we need from this cycle is not Q low, we need actually Q high. And this system, actually the refrigeration system, is the same as air conditioning system. So this is actually the same cycle as air conditioning system. So if you do have a split air conditioning system, we just put it in the wall. The inner part of the air conditioning system, inside your room you will do have what? The evaporator. So in this case I will absorb the heat from inside the room, and it is just fixed into the wall. The condenser in this case is outside the room. So we absorb the heat inside the room, Q low, take it and reject it outside. What will happen if I actually just flip this air conditioning system? I will make actually the evaporator outside and the condenser will be inside. So in this case the heat will be absorbed from the outside and then it will be rejected inside. So in this case what we get from this system, however it is air conditioning system, the same system, just I flipped it. I made the condenser inside and the evaporator is outside. So I'm doing the reverse in this case. We absorb the heat from the outside and reject it inside. So the system in this case is working as what? Is working actually as a heater in this case. So any air conditioning system can work as a heater, depending on what? Depending actually what you need from this system. Depending actually we need to cool down, then we can actually apply the air conditioning system. So we can make the evaporator inside, the condenser is outside. So in this case the system will cool down and it will work as air conditioning system. If I flip that, I make the condenser outside and the evaporator inside. So in this case I will absorb the heat from outside, from the evaporator, and then reject it actually inside the room. So in this case we can get Q high. However, it is the same system. So in this case the coefficient of performance of the heat pump is equal what we need from this system is Q high divided by what we give to this system, which is work net area, which is the same as Q high divided by Q net, which is Q high minus Q low. Just for this equation, if I just here I said minus Q low plus Q low, so this term will be equal to 1 plus Q low over Q high minus Q low, which is the coefficient of performance of the refrigerator. So the coefficient of performance of the heat pump is equal to the coefficient of performance of the refrigerator plus 1. But we said actually it is the same system. So this means actually when you do have air conditioning system, when it is working as a heat pump in winter or something, so in this case its efficiency or coefficient of performance will be higher than when it is working as actually as a refrigeration or air conditioning system during the summer. Okay. There is another parameter which is used in the English system of unit, which is called the energy efficiency rating. The energy efficiency rating is equal to 3.412 multiplied by the coefficient of performance of the refrigerator. Just as this constant is conversion of unit. So the energy efficiency rating, if you have, just in case if you have faced this term, energy efficiency rating for any refrigeration cycle is equal to 3.412 multiplied by the coefficient of performance of the refrigerator. This is regarding the application of the second law of thermodynamics for both heat engine, and we have seen how we can calculate the efficiency of a heat engine, and also we applied the second law statement for a heat engine, which says we cannot design a heat engine with efficiency equal to 100%. And the second application for the second law of thermodynamics on refrigeration system, and do have the second law statement of a refrigeration system, which says we cannot design a refrigeration system without work input to the system. We said the second use actually of the second law of thermodynamics is to calculate the theoretical limit of a system. So if you do have air conditioning system or refrigeration cycle, we can calculate the theoretical limit. Theoretical limit means we can calculate the maximum efficiency for heat engine, or we can calculate also the maximum coefficient of performance of a refrigeration cycle. And based on this, we can compare actually with the actual value and see actually how much is the difference. To calculate actually the theoretical limit, we just assume that actually any of those systems is a reversible system, where all of the processes actually within this system are reversible, so we don't have any kind of friction losses within the system. And based on that, we can calculate the maximum efficiency in case of heat engine, or maximum coefficient of performance in case of refrigeration cycle. And then we can compare it with the actual value. When the system actually, when all of the processes within the heat engine or refrigeration cycle are reversible processes, so we call actually this cycle as, the cycle in this case is called as Carnot cycle. So Carnot cycle is a cycle that consists actually of a set of processes. All of these processes are reversible, so we don't have any kind of losses within the system. So in this case, the efficiency calculated based on the Carnot cycle is the maximum efficiency. The coefficient of performance calculated also based on the Carnot cycle is called actually as the maximum coefficient of performance for refrigeration or heat pump cycle. As Carnot cycle consists actually of a set of processes doing a set of processes proceeding in a certain direction, and all of these processes don't have any kind of losses within the system. Those processes can be reversed processes, or processes also can go in the reverse direction. So in case of heat engine, we add heat at high temperature, reject part of this heat at low temperature, and then we can have work out of this system. If the process actually is reversed, if we go in the reverse direction, so in this case we can add heat at low temperature, and we can reject actually part of this heat at high temperature, and based on that we should have work input to the system. So as all of the processes within Carnot cycle are reversible, so either we can go in the direction from Q high to Q low so that we can get work in case of heat engine, or we can do the reverse, so we can proceed from Q low to Q high, but in this case we have to add input work. So Carnot cycle, as it is reversible, so it can be applied actually for both heat pump, heat engine, and also for refrigeration cycle. So in this case, Carnot cycle can be applied for heat engine, and also it can be applied for refrigerator and heat pump. We do have actually two characteristics of any Carnot cycle. For any Carnot cycle, it says actually if we do have two engines working between the same T high and T low, so we do have two heat engines working between the same T high and T low, so in this case they should have the same thermal efficiency. So eta thermal 1 is the same as actually eta thermal 2. So if we do have two heat engines working, actually this is heat engine 1 and this is heat engine 2, we do have work 1 here, and we do have in this case work out 2. So in this case, if those actually two heat engines are reversible, working between the same T high and T low, so they should have actually the same thermal reversible efficiency. Also, if you do have two heat engines, one is reversible, T high, and this is the engine, we do have work out, and this is actually T low. If this is actually actual heat engine, so the efficiency of the actual engine should be less than actually the efficiency eta thermal reversible for a reversible heat engine. And this is actually logic. In case of actual heat engine, we do have losses. So its efficiency should be less than actually the reversible one when we don't have losses within the system. And based on this, actually we can prove that. You can actually look at this proof in the slide. It will be in the first comment. You will find actually this ratio in case if we do have a reversible heat engine or reversible refrigerator or heat pump, or we do have Carnot cycle in general. In this case, the ratio between Q high and Q low is the same as actually the ratio between T high and T low. And this is actually by the condition that the system is reversible. And in this case, this condition actually is applied for both in case of heat engine and also for the case of heat pump. So in case of heat engine or refrigerator or heat pump system working on Carnot cycle, we don't have any losses within the system. So in this case, the efficiency is maximum for heat engine, and the coefficient of performance is maximum for refrigerator and heat pump. And at this condition only, when we do have the cycle is reversible, we don't have any losses. At this condition, we do have actually Q high, the ratio between Q high divided by Q low is the same as the ratio between the temperature. And based on that, actually for a heat engine, and this is actually applied for both heat engine and refrigeration cycle. In this case, we can calculate actually eta thermal reversible, or actually the maximum, we call it eta thermal reversible, or actually the maximum efficiency of the heat engine, which we said equal to work net divided by Q high. As this efficiency is maximum, so this means actually work net in this case is maximum, and the Q high in this case is minimum, which is the same as equal to, as we said, 1 minus Q low divided by Q high. And this is actually the difference. In case of actually the actual efficiency of a heat engine equal to work net divided by Q high. But the maximum efficiency is equal to what? Equal to the maximum work out divided by minimum heat input to the system. And we said actually in this case, as the cycle is reversible, so we do have Q high over Q low is the same as T high over T low. So in this case, the maximum or the reversible efficiency of a heat engine is equal to 1 minus T low divided by T high. And this is called eta thermal reversible, or it is called actually as the maximum efficiency of a heat engine. So the maximum or Carnot, this is called also the Carnot efficiency of the heat engine, which is the maximum efficiency of the heat engine, which is equal to 1 minus T low over T high. And also it is equal to work net maximum divided by heat input minimum to the system, and it is the same 1 minus Q low divided by Q high. This is in case of we do have a heat engine. In case actually if we do have a refrigeration cycle, so in this case the coefficient of performance for the refrigerator is equal to Q low divided by work net input to the system. This is actually the coefficient, the normal coefficient of performance. So the reversible one, coefficient of performance of the refrigerator reversible, or as we said maximum, or we call it actually the Carnot one, Carnot coefficient of performance, will equal to in this case Q low, as this is actually maximum, so it will be maximum Q low divided by minimum work input to the system. This is the condition actually to get the maximum coefficient of performance. So as we don't have any losses, so the work input will be minimum, and in this case the heat absorbed through the evaporator will be maximum in this case. And it is equal to Q low divided by Q high minus Q low. If you just divide it by Q low and replace it actually with the temperature, so you will find this is equal to T low divided by T high minus T low. And this is the coefficient of performance of the refrigerator, reversible or maximum, or again we call it as Carnot, which is equal to T low divided by T high minus T low. In this case actually you have to substitute this temperature in Kelvin, not in degree C. In the lower side, this is the temperature difference, it can be in Kelvin or degree C, but actually this value should be in Kelvin in this case. Like this also we can get the coefficient of performance for a heat pump, reversible or maximum, or as we said Carnot 1, which will equal to Q high divided by work net. As we said, this is Q high maximum, and this work net should be minimum, which is equal to Q high divided by Q high minus Q low. If we just replace it with temperature, just divide Q high up and down, so it will equal to T high divided by T high minus T low. And this is the case actually when we do have a heat pump. So when we do have a heat pump, the maximum coefficient of performance will equal to Q high maximum divided by minimum work input to the system, which is the same as Q high over Q high minus Q low, and then we can replace it with the temperature by this condition for a reversible Carnot cycle. Then in this case the maximum coefficient of performance will equal to T high divided by T high minus T low, and as again this should be substituted in Kelvin. In your exam or something, he may say actually he may not say actually we do have directly Carnot cycle. He may not tell actually this statement that the cycle is working on Carnot, but he may tell actually that we do have, let's say, a refrigeration cycle or a heat pump cycle working reversibly. So when he say actually the system is reversible, so this means actually the cycle is working on a Carnot cycle. So when he say we do have a reversible heat engine, reversible refrigeration cycle or reversible heat pump, so this means actually we don't have any kind of losses. So this means actually the coefficient of performance is maximum for refrigerator or heat pump, and in this case for a heat engine, in this case thermal efficiency is maximum in this case. You have to actually to consider, you have to make the difference between heat engine and refrigeration and heat pump. In case of heat engine, we don't have coefficient of performance, just we do have the thermal efficiency, and this thermal efficiency should be less than 1, okay? Even the maximum value should be less than 1. For a heat pump or refrigeration cycle, we do have coefficient of performance, and in most of the cases, this one will be greater than 1. And this one, coefficient of performance of the heat pump equal to 1 plus coefficient of performance of refrigerator. This one is a positive value, so this means always the coefficient of performance of the heat pump should be greater than 1. Okay, but the thermal efficiency should be less than 1 based on the second law of thermodynamics. But in some cases in your exam or something, he may tell you actually calculate, let's say you do have a heat engine, he may tell you calculate actually the maximum work out of this system. So when he tells you actually calculate the maximum work out of a heat engine, so we do have in this case working out is maximum. So this means the efficiency is what is maximum in this case, and we can apply this condition Q high over Q low is the same as T high over T low. So in this case the maximum efficiency is equal to 1 minus T low divided by T high. So this condition 1 minus T low over T high or Q high over Q low is the same as T high over T low is only applied when we do have Carnot cycle. Otherwise we have to use this cycle. Okay. So if he told you calculate the maximum work out of a heat engine, so in this case this mainly needs to calculate the maximum Carnot efficiency, which is equal to 1 minus T low over T high. It will be given to you T low and T high, then we can calculate the maximum efficiency. We need to calculate the net work out. So in this case, this Q high should be given in this case. Either it given directly, it is given directly, or he may tell you actually use a condition at the inlet and that outlet of the heat engine. Then we can calculate Q high. But let's look at actually if the conditions are given for a heat engine or refrigeration cycle in any of the devices, and we need to calculate, let's say, Q high or Q low or something. So in this case, if you look at actually the heat engine, we do have the pump and we do have the condenser. Here we do have the turbine. Okay, so this is the boiler, turbine, pump, and then we do have condenser. We do have Q is rejected from the condenser and heat is added here in the boiler. This is in case of we do have a heat engine. So in this case, in actually steam power plant or something, in this case the working fluid is steam. So if he give you the condition before the boiler, let's say B1, T1, here B2 and T2 are given. So in this case, from a steam table, then we can calculate H1. From a steam table, we can calculate H2. And then we can apply the first law of thermodynamics for this boiler. Then we do have Q dot. This is a steady flow open system device. So Q dot minus work dot equal to M dot H2 minus H1 plus V2 square minus V1 square divided by 2 plus GZ2 minus Z1. Usually we do have the inlet and the outlet of the boiler at the same elevation, and usually we neglect the change in kinetic energy. For this boiler we don't have work, so in this case Q high in the boiler should equal to M dot multiplied by H2 minus H1. So in this case he may give you the working fluid, give you the condition at the inlet and the outlet of the boiler. So in this case we can calculate Q high M dot multiplied by H2 minus H1. Let's say this is 0.1 and this is 0.2, this is 0.3 and this is 0.4. Also like this, similar, very similar. He may give you the condition at 2 and 3, then we can calculate work out of this turbine. The work out of the turbine, rate of work out, will equal to, also you can apply the same first load, will equal to M dot multiplied by H3 equal to H3 minus, or this is positive H2 minus H3. So using the table you can calculate H3 by as the condition at point 3, and also condition at point 2 we can calculate H2. So if I need the work out of this turbine we can calculate also. Also in case of condenser you may be given actually here also the condition at point 3 and point 4, so Q dot condenser, which is called the Q dot law, will equal to M dot mass flow rate of steam multiplied by H4 minus H3. So either he will give you the condition at the inlet or outlet for any device, and in this case you can calculate either the heat transfer or the work, and then actually you can just substitute in the thermal efficiency, then we can calculate what we need. If it is needed to calculate the work, then we can calculate Q high using this relation. If the condition 1 and 2 are given, then we can calculate the maximum work need, and this can be calculated through the substitution with the temperature. Like this in case of heat engine. In case of refrigeration cycle, also the same concept is applied. In case of refrigeration cycle, let's draw also the cycle. So in this case we do have, here we do have the condenser, and here we do have the compressor, here we do have the evaporator, and here we do have the expansion valve, and again the cycle is proceeding in this direction. So let's say this is point 1, this is point 2, this is 3, and this is 4. Also, for this case, it may be given for you of condition. In this case, the working fluid in most of the cases, we do have refrigerant 234A. So we do have the table. If the condition B2, T2 are given, then we can calculate H2. Here, B3, T3, then we can calculate H3. It's not a condition to have pressure and temperature. Maybe pressure with any specific property, or temperature with any specific property, or pressure and temperature, depending on the case. Then we can calculate H2 and H3. Then we can calculate Q low, which will equal to M dot multiplied by H3 minus H4. So in case of the condenser, if the condition 4 and 1 are given, so in this case Q dot high will equal to the mass flow rate of the refrigerant multiplied by H1 minus H4. So if the condition are given, then we can just calculate Q high and Q low, then we can substitute in the coefficient of performance. In some cases, he may not give you actually the condition 1 and 2. He may say we do have a condenser. Let's say it is cooled using water or something. So water is coming at temperature T1 and leaving at temperature T2, and we do have the mass flow rate of this water. So the heat rejected from this condenser is absorbed by this cooling, let's say cooling water or something, coming at T1 and leaving at T2. So in this case, the heat lost from the condenser, which is Q dot high in this case, will equal to the heat absorbed by water, which will equal to M dot water multiplied by H2 water minus H1. H2 minus H1 for water, so it will equal to M dot water, CB water multiplied by T2 minus T1. So T1 and T2 will be given. CB water you can calculate, okay, which is, or you can just take this value 4.28, or you can calculate it as the average temperature, T average from table, I think table A3. We can calculate it for water. It's around 4.18 kilojoule per kilogram Kelvin. And mass flow rate of water will be given. Then we can calculate also Q high, which is the heat rejected in the condenser. And again, we can substitute in the coefficient of performance relation with this Q high, and then we can calculate actually what we need, either the work or the Q low, or we need to calculate the efficiency itself. So it's okay by this chapter. This chapter is almost done with most of the ideas are presented. So thank you.